Wagner from University of Rostock, and he's going to talk on KL leaf.
Thank you very much. First of all, I would like to take a fraction of my time to thank the organizers for the support and the opportunity for me to speak here in Cambridge. This is actually my second talk here in Cambridge, the first being not at the September workshop, but a combinatoric seminar back in 2004 when I was still doing a PhD over there in Pavilion C. But as of January, I've changed to theoretical computer science, and I'd like to talk about KL leaf powers and leaf powers today. My supervisor, Andreas Brandstedt from Rostock, he gave a talk on K-leaf powers in September. And initially, I thought I'd just give a natural continuation of his talk. But I realized that many of you haven't been here in September, and I think I will give a proper introduction to them also. So, first of all, by Kim and Wono, we've got, well, probably most of you, well, you will all know about that the trees play an important role in trying to describe the history of species. The genealogical history of life is usually represented by a bifurcating leaf-labeled tree. With bifurcating, we take degree 3 in the internal vertices. So this, then we carry on with the phylogenetic tree being rooted at the most recent common ancestor of a set of taxa, and each internal node is labeled by a known or not yet known ancestor. So there has been another notion of a phylogenetic K-root introduced by Lin, Kearney, and Jiang. Phylogenetic K-root and Steiner K-root, which is a variant of it. At the Computer Science Conference ISAC 2000, we've got a finite undirected graph G, and this is a phylogenetic K power in that sense. If there's a tree, which is a K root, and that basically must have internal vertices of degree at least 3, and now this is the key point here, that we have the leaves of the tree representing the vertices of the graph, and we've got the distance condition, which is very important. So we've got an edge in the graph G if and only if the corresponding leaves in the tree have a distance of at most k. This is for any given k. And this is not quite well what you get by considering a tree, an evolutionary tree, given a set of species, but this notion is, as I wrote that here, is based on the idea that sequences of small distance or respectively large distance should have a small or a correspondingly long distance or the respective leaves in the tree, in the phylogenetic tree. And distance between sequences is, well, the number of places where they differ. It's the Hamming distance, and the distance in a tree is just the number of edges of the unique path joining two vertices. So the problem, of course, is that given a graph G, how do we tell that this is a phylogenetic K, or is there a phylogenetic K root? And for different Ks, there are different answers. For small k, for k at most 4, in 2000 there has been a linear time algorithm given by Lin, Kearney, and Jiang. And for k at least 5, the problem is open. So the existence, yes, of a root. So the same thing, as I said, mentioned earlier, rather than just specifying that leaves must be the corresponding vertices of the underlying tree for a graph, we can have any subset of the vertices of the tree, and that would be a K-Steiner root. But let's concentrate on the simple case of leaves first. Leaf powers, what are they? Basically, so here's the definition. but what they really are is you take a tree and take a power of it, like it's square. That means you connect all the vertices which have a distance of at most 2 in the tree, and then you consider the induced subgraph by its leaf set, by the leaf set of T. This is what is hidden in this definition here. Graph G, and here leaf set V. So the V of set of vertices of G is hidden in the vertices of T, and this is precisely the leaf set of T. And here we've got the distance condition. So we've got the leaf power. So in general, this was for K. And a leaf power, a graph is a leaf power if it is a K-leaf power for some K. This is quite natural. So, and as I said before, leaf powers is what we get by taking trees. We take any tree, T, take a power, and then have a look what is the graph induced by the leaf set of T. So this is a straightforward observation. If you take trees and then the second power, then only leaves with a common parent can be joined. So we will get unions of cliques. Now, what about three-leaf powers? This is just a very simple case of a tree. In fact, any tree is a three-leaf power, but where do we get the root? So we've got those 4 nodes, and this is a three-leaf root, a tree, where 1, 2, and 3, and 4 are the leaves of that graph. And any 2 vertices that are connected in the graph have a distance of at most 3 in the tree. So we get that graph. And diamonds can be realized. Diamonds are three-leaf powers because have a look at this root. So this is a tree, and any edge here corresponds to a path of at most length 3 on the right-hand side. Now, having introduced the class of leaf powers, we would quite like to know what they are. Can we place them in between known classes? And chordal graphs, which this notion has come up in talks before, chordal graphs are those that haven't got any cycles, basically. So there's no chordal cycle of length 4, C4, C5, C6, and so on, CK for K at least 4. Chordal graphs are a nice class of graphs, have been studied a lot. They have got properties, they've got clique separators, and there is a clique tree, and the graph is a chordal graph, and if and only if there's a simplicial elimination ordering. We've got the fact that chordal graphs are precisely the intersection graphs of subtrees of a tree, and it's going to turn out, well, that leaf powers are chordal graphs. But not only chordal graphs, also strongly chordal graphs, but this is what we are going to get to. I mentioned the notion of power before, but this is just another slide to tighten this up. I mean, this is just, you have G, and then the kth power is, you add any 2 vertices which had a distance of at most K in that connected graph, connected I should have said here, gets an edge in the kth power. And this is then denoted the kth power of G. Right, and this is now just simple observations. K leaf power is an induced subgraph of the kth power of a tree, in particular induced by the subset, which is the leaf set of the tree. And every induced subgraph of a K leaf power is a K leaf power. Yes, this is a simple hereditary property. Powers of trees are chordal. These are suns. There's the notion of K-sun. You've got a clique in the middle, or these are split graphs with the 2 classes, the complete, the clique, and then independent set, done here by the green vertices of the same size, and they are joined by a path in that manner to form a sun. And if those graphs are forbidden also, then chordal graphs are then strongly chordal. So strongly chordal graph is a chordal graph which is also sun-free. And there has been a series of papers about that fact that powers of strongly chordal graphs are themselves strongly chordal. And since trees haven't got since trees haven't got cycles and they haven't got suns, obviously, trees are strongly chordal, and therefore their powers are strongly chordal, and their induced subgraphs are also strongly chordal. So we already know that leaf powers are strongly chordal. However, again, there has been work done by B. Belnix, Deering, Royn, and Love, who showed that not every strongly coiled graph is a leaf power. So unfortunately, we are not quite done. This graph, for example, I mean, this isn't obvious why this is not a leaf power, but I would just put it there into the talk to give you an idea of, well, I'm claiming that this is not a leaf power. And it actually came up in that paper here. Right. What about 3 and 4 leaf powers? If everything is so, no, I'm not saying that just because it's very complicated. So these 3 and 4 leaf powers, there have been recognition algorithms of order n cubed by Nishimura, Rakte, and Tidikos, who also introduced that notion of k leaf power. And as we can see here, for k at least 5, the characterization is open, and leaf powers the characterization of leaf powers in general is also open. I mentioned critical click graph of some graph. A critical click is a maximal click module of G, and the module is a subset of the vertices such that for any other vertex outside, it either sees all the vertices in the module or none of them. So here's an example. So you've got a graph. What about the click modules? The maximal click modules by inclusion maximal. So here, for example, for any other vertex outside, either it sees all the vertices or none. And this is, okay, these are all the critical clicks. And now if we draw the critical click graph, this is a tree. And this is not a coincidence, because we started off with a 3-leaf power, in fact. So 3-leaf powers, there's yet another characterization for those. This is a bull, a dart, and a gem. And the bull, dart, gem-free chordal graphs are precisely the 3-leaf powers. And a theorem by Dom, Guo, Höfner, and Niedermeyer from 2004 precisely states this, what I was just claiming. And the critical click graph of G is a tree. So then the complexity was still a bit dissatisfactory. This has been brought down to linear time by Brandstedt and Lee. And we see here that 3-leaf powers are precisely what you get by taking a tree and then substituting clicks into the vertices of it. So it doesn't seem to be too complicated. 4-leaf powers. This is a set of graphs that are needed to describe 4-leaf powers without true twins, without 2 vertices that are connected and have got the same neighborhood. And 4-leaf powers are precisely the chordal graphs that haven't got all these as induced subgraphs. It's a theorem by Rautenbach from 2004. And this was refined by Brandstedt, Lee, and Schrie. So we've got 2 connected basic 4-leaf power. 2 connected is needed in order to describe the blocks. This is equivalent to G being the square of some tree. So what is going on here is that we, rather than having trees before, we have squares of trees in the 2 connected components. And the graphs G6, G7, and G8, which do not come up here, are responsible for what happens, how to glue the 2 connected components together. So, okay, this is yet another theorem. I think I should press on a bit. So, because after all, I want to mention what KL leaf powers are after all. So, just some more results. Ptolemaic graphs is a known graph class in graph theory. Interval graphs is a widely studied graph class, and they turn out to be leaf powers, which is a result by Brandstedt and Hund. Then this was improved because rooted directed path graphs is yet another class of chordal graphs, and they include the Ptolemaic and the interval graphs, and they're also leaf powers by a separate proof. And then this is about comparing k leaf powers and k+1 leaf powers, because it's a very simple observation to see that if you've got a k leaf root for a graph, then by subdividing all the edges that contain a leaf, you get a k+1 leaf root. All the distances get increased by exactly 2. So this is very simple. K is a k+2. But what about this question? And 2 leaf powers are 3 leaf powers. 3 leaf powers are 4 leaf powers. This is a fact. But for all k larger than 3, this does not hold anymore. This is simply a structure. Well, this is an existence result, and well, it's affect. So KL leaf powers. This is the same setup. An edge, if the distance is at most if there's an edge in the graph, then the distance in the tree is at most k, and that L corresponds to the case if that is not an edge. So at least L. K leaf powers are k plus 1 leaf powers, and of course this is a specialization of k leaf powers. When we for any given k, then in any larger L, we get a subset of the k leaf powers. And why is this important? Why is this necessary? Or I mean, anyone can come up with new notions and try to push the subject further, but does it make sense? And it only made sense to us because there's a paper by Kennedy, Lin, and Yan that was dealing with strictly chordal graphs. Another graph class, that subclass of chordal graphs, and they turn out to be exactly the 4-6 leaf powers. So, okay, those 4-6 leaf powers. What I said here is that those 4-6 leaf powers are obtained by taking block graphs and substituting clicks into the vertices of the block graph. Similar to what happened with 3-leaf powers, you have trees and substitute clicks into the vertices. We have block graphs here. And what is a block graph? A block graph is a connected graph with its two connected components being clicks, or blocks in other words. So here you've got a click and there, click and there, click, and they're all joined in a tree-like manner by a cut vertex. And if you substitute a click into a vertex like this, doesn't matter, it still stays a block graph, as you can see, but if you, for example, substitute an edge in there, this is the result. So this is an example of a strictly chordal graph, which is a 4-6 leaf power. I would quickly want to say that those 2 and 3 leaf powers and the 4-6 leaf powers appear infinitely many times as KL leaf powers, in the sense that this happens for infinitely many pairs KL. This also happens for 6-8 and 8-11 leaf powers, where characterizations are known. This becomes a bit more complicated even. 9 forbidden subgraphs, and this deals with that case. I just want to give you an idea of what has been done in the case of KL leaf powers. Everything to the right is known. All the colored classes are known. I mean, known in the sense that there is a characterization for it in terms of forbidden subgraphs, or in terms of what it is, how to obtain them. And they then again imply at least polynomial time algorithms to recognize them. And what we get here for 5, 5, 6, 6, 7, 7, 8 are all the leaf powers right on the left, and 4, 5, actually this also deserves a color because this is known. From here it starts becoming fuzzy, and I'd just like to give a few open problems. Given that our K leaf powers, well, K leaf powers are KL, no, KL leaf powers are K leaf powers, this is all the same notion, basically. This is just a specialization. So for K at least 5, we want a characterization, and for leaf powers in general. And then the complexity of recognizing K leaf powers is unknown. So you see that for K is equal to 5, the complexity of recognizing is at least known. There's a polynomial time algorithm of n to the third, and where n is the number of vertices, given by Ko and Chang, which is a paper that appeared in the WG this year. And then, okay, characterization of further KL leaf power classes for, well, for example, 7, 9, as you can see here. This is not known. And why is this interesting? Well, it might give insight, a proof of this might give insight and to how to approach the 7 leaf powers, for example. And I'd like to thank you for your attention. Yes, please.
Computing these distances, you're just counting edges in trees and graves.
That's right.
Is there a notion, you looked at the possibility of having weights on the edges?
Weights, we can get all rational weights by simply subdividing the edges. But we haven't actually looked at what happens if we take irrational numbers in order to get other weights.
Okay, but
If you have a phylogenetic tree with or without weights, and you look then at this other graphs you construct on the set of leaves and so on, according to your rule, does it give any kind of interesting insight into the structure of the original data? So you said it should get together sequences that are more or less similar.
Yes, I think if we had all the information, if we had just for a given k, the information would be rather limited. But if we had more, like for all the k's, then I think it would be possible to reconstruct the information that is hidden in the tree if it exists. But yes, as you see that.
Or turning it the other way around. When we want to reconstruct phylogenetic trees, and if we have them, we are happy with them. But sort of these graphs you are considering are some kind of weak invariant of the tree.
Yes.
You get some graph that does not necessarily come from a tree, the graph you get, and if so, I don't even know whether they are unique or whatever. The trees you use to get your graphs. But can you maybe use phylogenetic data to go directly for these derived graphs? These powers, or how you call it.
I would be interested in hearing about.
You should tell us.
Yes, I know, but the motivation really is well. Once we had a paper and we were interested in Cayley powers, that we tried to press on with the results there. But how to incorporate or to use it to get some useful in a sense in the applied world information out of it. That is something I'm still looking for.
Okay.
I have a question. If you give a G and you know all its power, can you reconstruct?
That is, if you're given a graph and a k and you want to find its kth root, that's in general NP hard or NP complete to find.
No, I mean, if you give a G, then you have all its information of G1, G2, Gk. I mean, infinite. Can you reconstruct G?
If you've got g squared, g third, g, all the
Yeah, I mean,
powers,
all power.
apart from g, of course.
Yeah.
That's a good question. Usually, if you're just given one power, it's not going to be unique and also difficult to find. For trees, if you know that it's a power of tree, or you can check in linear time actually whether it is a power of a tree, and then also get a root. But well, since we're dealing with trees, yes, it is possible.
For G.
For trees, it is possible, yes.
Okay, well, let's thank the speaker again.